delay. Our today's session is devoted to Vinberg's special Connie, and our speaker is Professor Dmitri Alekseevsky. Dmitri, please.
Okay, thank you. So may I start?
Yes, yes.
Okay. So I will speak about homogeneous convex cones. It's my traditional subject, and I will recall basic definition, and then we'll discuss some very interesting but not very clear application to information geometry, especially based on two papers by Yuri Manin, with one paper with one collaborator, another paper with two collaborators. In fact, which are very interesting, but it is a preprint, and it seems that there are many strange claims, and some probably it is not the final version, but nevertheless, the subject is very important because it has, in fact, it is based on discussion about future theory, which has a different name. So, for example, Manin called it landing world of geometry geometrical landing of information, something like this. There are also named information geometry, but information geometry is already occupied because there are theory developed by Chintsov and Amari, but some people extend this to some till now not created new theory, which have described the information. So it is, of course, very ambitious project, like construction of some thermodynamic. So now it is a unification of many different subjects, like thermodynamic, statistical physics, information geometry, Vinberg cone, Frobenius manifold, Jordan algebra, but in one of the paper, Manin discussed also application to zeta function of Riemann, but I did not even try to read this. In fact, it's related with almost all mathematics, but it is till now pseudo-Keller geometry and many other things. But I start from very elementary object. This definition of convex. Спасибо. Convex cone in vector space. So this is cone means it is open, first of all, open domain, which is invariant under multiplication by group R plus. So this is cone. And if it is convex, this means that we have convex open cone. So simplest example is R plus in R. And also that first example second example, direct product of cone. So if you have V, we have cone, I denoted by V, cone V1 into V1 and V2 into V2. So it assumes that it is a convex cone, then V1 cross V2 in V1 plus V2 will be again a convex cone. Convex cone, so when we have such convex cone, okay.
Can you give us a less elementary example?
Yeah, of course, yes, I will give less elementary example. So first of all, of course, this implies, first of all, that we have R plus in power n will be a cone into Rn. So it's very, very important. Practically for almost all information geometry at the beginning was, and a big part of mining paper devoted to this case. But this is not all. Then we have considered that, assume that we have K is division algebra, that is R, C, H, O, division algebra. Then we can consider, and we consider a vector space V equal K.
Maybe I don't understand something. So, for example, if we take n equal 2,
yes,
it will be the first quadrant. Yes?
Yeah, exactly.
But it is not open.
No, but R plus means open. So
yes, R plus
no,
is open.
okay. So this is okay. So this is cone.
Yes, of course, sure.
Okay. So we consider V equal K in power n. Of course, it can be considered as a real vector space. And then okay, this. Sorry, no, this is sorry, no, this is not. We consider a K of n. It is matrices. So this is a standard notation from Spinor geometry. So it is matrix n by n matrix with entries in K. And in this case, we can consider. Sorry. No, sorry. No. So let us consider another notation. We consider Herm n of K. It is a space. It is in matrix n of K. It is Hermitian matrices over K. So for K equal R, of course, it's only a cone of symmetric matrices, and then then it is some generalization. But everybody knows what are symmetric Hermitian matrices. So it's linear, K linear in one argument and anti-linear in other argument. And then in this case we have cone of which maybe I call it. I shortly called H. V n of K, and this is cone of positive defined matrices in K. So it means positive defined. For example, the most important example, it is people who do some statistics and other applied mathematics. They one of the most important object, it is cone of positive defined real matrices, n by n real matrices.
You will give at least idea why these cones have relation with or you do, it is not topical.
Relation with information geometry?
No, relation with thermodynamics.
With thermodynamic?
Just to give idea, because it's very...
it is because this cone this I explained that it's very simple. This cone, it is cone. It is cone of probability distribution. Probability distribution. So I think in statistical physics, probability distribution, you can consider also quantum version. About quantum, I say very few words, but it is
classical. It's classical. It's
yeah.
Probability distribution.
Yeah. And but in one of this paper, it was developed. In fact, before even it was developed by one of collaborator of mine from United States, who is Marcoli. It's a woman. Marconi. Okay. And but in this joint paper, it is discussed. Yeah, okay. So this, I think this already sufficiently interesting example. And now what are some interesting property of the cone? So we say that cone V, of course, convex cone. By cone, I always understand convex open cone. Sorry, I forget one condition, important condition, that there is no line, real line, L inside V. So, for example, half plane, no line.
What it means, no line? Straight
line, no straight line. For example, all space is not a cone. So plane is not a cone.
Okay.
But for example, but in principle, half plane, open half plane will be a cone because this is not line. You consider open. Yeah, this is important because yeah, no, but all this, of course, some real cone. And then assume that we have such cone in V. Then we can define group of automorphism of V, which is a subgroup of the GLV, a linear group of linear transformation, such which preserves this cone. Okay, so then of course all this cone are a cone is called homogeneous. V is homogeneous if this group out V act on V transitively. So in this case, the cone will be homogeneous manifold, and stability will be so subgroup which preserve one point. It will become compact. For example, so let us consider. Okay, so R plus, of course, it's clear. But if you consider this cone of Vn of k, then okay, we can write that Vn of R, we call it also Pn. So cone of positive divine matrices, it can be considered as homogeneous space GLV modular, no, maybe GL plus V, plus means that preserve there is determinant 1, modular S or V. So this homogeneous manifold is really very, very important. And more precisely, it can be decomposed into direct product of R plus multiple identity matrix cross SL V mod S or V. And so this both are yeah? Plus means determinant one. Sorry, means determinant one. Yes. Plus connected component. Connected component.
Positive.
What?
Positive determinant.
No. It is group. It is not element of the cone. It is a linear group.
Yes.
Linear transformation. So any linear transformation, of course, action. Maybe I forgot action. So A applied to X, where X is this Hermitian matrices. A applied to X equal A X A star. So this is it is transformed as Hermitian form. It not as operator, but as Hermitian form. And so everybody knows that any positive defined matrix can be transformed by this transformation into identity matrix.
But
Yes.
Plus denotes positive determinant or determinant equal to 1. Then it is SL.
No, positive. No,
Positive.
It's important because in other case, determinant will be multiplied by square of determinant of A. But we want to transform it into identity matrix. So we need scalar multiplication. So for example, lambda applied to X will be lambda square X. And then we can also, of course, SL action of SL also very important. But it defines some hypersurface, very important. Determined hypersurface, which is very important. Okay, so all this, of course, all this cone are homogeneous. So here we have a cell, then we have S R. If we speak only about this hypersurface, then it will be UN or SN for complex case, SPN for quaternionic case, and E6 for this special cone. Yeah, I forget to say that if K equal O octonion, that N must be equal to 3 only. Only to 3. Yeah, and okay, and maybe I give some more example. Then it will be some last example. This is a following cone. So we consider cone of matrices. I call it, how we call it, V2 of maybe W equal, if you want, okay, Rn. It is by definition. This is by definition set of all matrices X of such form X1, X2, V star, where X1 is a positive number, X2 is positive number, and V is element of any vector of Rn. And this is a transpose vector. So this cone, and of course, sorry, this is not a cone. No, it will be cone. Then, of course, if it is a cone, then we need extra condition that a determinant of this X, which of course obviously define X1, X2 is product of number minus V star. No, V star we have scalar product. Yes, so it is well defined. Determinant of X must be positive. So this cone is called in physics is called a spin factor. Spin factor. It was, I think, it was firstly defined by Wigner, Jordan, and von Neumann in 1934. When
so
they,
one row one column, and one element.
No, you see, it is 2 by 2 matrix, but
Two by
V
two.
is 2 by 2.
2 by
It is
2,
2,
okay.
no, 2 by 2 matrix, but V is vector.
Representation theory or no?
It is a classification of Jordan algebra. And this is, and then they consider this as cone of a state, a mixed state. So this, in fact, this paper was origin of, in fact, all this theory and all application. And now practically all return to this idea by Wigner, von Neumann, because they consider statistic. And now people consider all this, but from point of view of information geometry, which almost the same.
I'm sorry. So if this is 2 by 2 matrix, then V is a number. And
No, V is not. V is a vector. No, this is main. This first example of Vinberg cone, because Vinberg in some sense generalized this example.
Why V is a vector?
Can it be 2 by 2?
No, V. No, okay. This two number and this vector. This conjugated
But
vector.
how can it be 2 by 2 then?
What? No, you can write as matrix, but entry of matrix are vector. And this, in fact, idea by Vinberg that you.
What's the definition of a determinant?
I say determinant is x1, x2 minus v star, but v star is vector and covector. So we have pairing between vector and covector.
It's not obvious that it's
Yeah, of course. No, of course, no, of course. But again, it was. But features also is they have even some name. They define a metric.
V star means it's a cotangent vector. It means it's a living in the V star, or it's just. You mean
I don't know what.
V is in a vector space, and V star is in the dual.
Dual vector space, exactly. So this is column and this is row. So of course.
You won't say one sentence. It was stopped. It was we want to say that it is you was continue. Okay, вы что-то хотели сказать. You want to say okay.
Yeah, look, please. What что?
No. You wanted to say that.
No, I want to say that this is a homogeneous convex cone. No, yeah. Oh, I forget. This physically, this cone is Lorentz cone. It is cone of. Yeah. This of course. This space is canonical isomorphic. This space called how do you call it? Herm 2 of V. This space is isomorphic to R1n, R1 n plus 1, R1 n plus 1, with respect to the metric G, GXX equal minus determinant of X. So this you can find in any, when you, everybody knows that Minkowski space, a 4-dimensional Minkowski space can be considered a space of 2 by 2 Hermitian matrices.
Yes.
In this case, V is a number, a complex number. Sorry, in this case, this 2-dimensional space. So this is right this, okay. Some X1, X2, Z bar. So this is solid Minkowski space. It is, as I know, R1, 3 standard Minkowski space. But then you can consider generalization, and then you have n-dimensional Minkowski space. Okay. So this is spinor. This spinor is due to this is called. In fact, I don't understand why they call it a spin factor. Of course, for dimension 1, 3. Yes, you can consider, because this is, in fact, you consider a spinor, it is C2, and then in terms of C2, you consider Hermitian matrix as C2. This I understand. But for high dimension, I don't understand why they call it spin factor, but this is only definition.
And it is Vinberg cone. It is, you say that it's an example of Vinberg cone.
Yeah, I will give definition later. This special Vinberg, he come to this construction from very different idea. Some consider some idempotence, but at the end he get such very nice, very important construction. And so now so this was, I read this only from this Mannion paper, that this construction is very important for Frobenius manifold, this Witten, the Verlinden, all this associated equation, and all this. So this closely related with such Vinberg cone. Yeah, Dubrovin theory of Frobenius manifold. And also important, but for why it is important for information geometry, of course, it is clear because it's practically main object of information geometry. It is a manifold of probability distribution, and this is manifold of probability distribution. Okay, so now, so all of them they are homogeneous cone, and now okay. Now we remark that, okay, maybe I say, now I recall this paper, this Jordan, Wigner, and von Neumann. They give classification of Jordan algebra, which was proposed by Jordan as a space which describe no observable space of observable of in quantum mechanics. So what is Jordan algebra? So A with multiplication. So finite dimensional vector space with multiplication, which is associative and commutative, is called Jordan algebra if it is satisfy also such identity A square dot B dot A, like this, equal A square dot B dot A for any AB. So then it is Jordan algebra. Of course, it's very unclear this definition, but it is important. In fact, according to what?
It follows from associativity.
Not associative. No, this is special associativity. No, it is associative when also we have this entry. If you have ABC, it will be not associative. Only this.
You have already said that it's associative. You said it is associative.
It is, first of all, it is power associative. So A in any power, it is really.
You have right.
You know that it is associative.
I don't know. This it is associativity only for this special case.
Вы писали буквально, что вы видите, вы асот написали. Вы имели в виду ассоциативно. Вы буквально писали там.
No, I don't understand.
We neither. You know that this is associative.
Sorry. Non-associative. Yeah, non-associative. No, sorry. Non-associative.
It was a statement that
Commutative. AB equal BA.
operation xy plus yx. I remember at least in quantum mechanics. Xy plus yx.
Yeah. I explain. Yes.
But what's the relation with
Just a moment. I just now consider this. And then, according to of course, it's impossible to classify all such Jordan algebra, but it's possible to classify Euclidean or compact Jordan algebra, and we call it Euclidean or compact if trace of LA square is positive for A not equal 0, where LA x equal ax, of course, equal xa. So we have the Euclidean scalar product in this algebra. Then it's called Euclidean. And then any Euclidean can be decomposed into direct sum of non-decomposable. So sum of two Euclidean algebra will be Euclidean algebra. We consider only indecomposable, which cannot be written as sum of two such algebra. Then, according to this theory, the list of indecomposable Euclidean Jordan algebra are exhausted by Herm n of k. Of course, if k equal O, then n must be equal to 3, and this how it is called, V2 of Rn, and this spin factor plus spin factor, So spin factor means Minkowski vector. Minkowski, what is spin factor? Minkowski vector space with multiplication, with trivial multiplication. So I explain what is this algebra which gives Lorentz cone of time-like future directed vector. So we consider R1n. We consider this as R, call it T. This is better say N1. So it is okay, then maybe better to write. It will be Rn, this Euclidean part, plus RT, where T scalar product with T equal -1. So time scalar square. This is time and this is space. Such decomposition. And then this T, I call it E0. I call it E. And then this E is identity. So E, of course, either E as multiplication is identity. Then it's remain only explain what are product of two elements from this Rn, because okay, obvious product this with this, of course, okay, x dot E equal E dot x equal x. Then it's remain to explain what is xy. Xy, what a possibility. Xy, it is scalar product xy identity. That's all. So this is spin factor. No, E is 1. So okay, instead of E, I call it maybe better. I call 1. This 1. This. Well, this is this most important for physics, and then according to John Bias, which very interesting, really physicist, and also I very recommend who is interested in information geometry. According to, I think it's not only my opinion, that the very important future theory is a theory of this. Manin called also it geometry of information. There are different name, and Bias call it information geometry. And then Bias, he has some site. Okay, maybe I read his name, John. He has, and then he has site which called information geometry. And I think this is a paper of 21st century, because it is a paper started in 2010, and then it is till now, and blah, blah, blah. continua. And this interactive paper. So this means that everybody, there's some special special place where everybody can write comment, question, and so on. And other give answer on this question, repeat, and so on. And also in this paper, probably if this paper, there are some written, how it's called, when you click and then appear some text, how it is called. No, you written in blue. When you in blue, you click blue, and then it's already you get some hyperlink. Yeah, hyperlink. Yeah. So there's a lot of hyperlink, and so because if without this hyperlink, maybe it will be some 1,000 pages, but this is all hidden in this hyperlink. So if you want to understand what is some, I don't know, some Kullbach some what's called Kullbach label divergence. You click and then you get a paper about Kullbach Leibler divergence and so on. Okay. So I very recommend this paper. But then also he has some very interesting paper, which he called division algebra in quantum mechanics. And second paper with his colleague, which is called division algebra and supersymmetry. And then, according to his point of view, all algebra which are important for supersymmetry, it is rank 2 Vinberg cone. That is, this means that a special case of this is too general for him, and he consider special case when it is you have V2 of K, where K is division algebra. In other words, it is algebra of Hermitian matrices, 2x2 Hermitian matrices over K. So here vector is must be a real number, complex number, quaternions or octonions. And then he explains that only such, he gives some very nice physical interpretation in terms of quantum mechanics and practically in terms of Jordan Wigner approach, very nice. But I think it is too restrictive because in our paper with Cortez, we generalize this for 3x3 Vinberg cone, which I explain what is it later. But for 2x2, it's also very, very nice. Okay.
Bias would be with zeta Riemann zeta functions or no?
In fact, I did not read. I have no time to read, and also I don't know.
I just look
I don't know how it's related with zeta function, but you can find in this joint paper with
yes, thank you.
Marcoli and other girl. Okay. Yes. So now I state this theorem by Jordan and his collaborator, and now I state another theory. Maybe it's two. This theory by Vinberg and Köcher. And to state this theory, I need a new notion. So if you have V is convex cone in V, then we can consider theory of duality, very, very important. Then we can consider dual space V star. And in V star, we can define also cone V star in this V star. which is defined as following. So it consists with all, call it maybe psi, one form, which are positive on V. So dual cone. And then one can check that it will be, of course, convex cone. And if V is homogeneous, then V star is also homogeneous. And in this case, Vinberg also proved that always exists the group of automorphism, which is not necessarily simply transitive, can have stability subgroup, like in this case, so you have stability subgroup. But in this case, you can consider upper triangular matrices, which will act simply transitively. Yes, so this means that any positive defined matrix, for example, let us consider this case. Any positive defined matrix can be canonically decomposed into form A dot A star, where A belongs to, they call it Vinberg group G, which consists of all matrices of the form. So it will be some alpha 1, alpha n, something, here 0. So this is theorem of linear algebra. Any positive defined matrix can be decomposed. Of course, it immediately follows from the fact that any matrix can be, so decomposition into product, it is a Gauss method.
Just to fill the definition, for our trivial example, when our cone is the first quadrant,
yeah,
what will be the dual?
No, for dual will be, no, in this case, it is self-dual. Identify with, yeah, but just I give definition, this very important definition. So, okay, so if this homogeneous, then also exists this upper triangular matrices, group of upper triangular matrices, which are simply transitively. And this, of course, very important, very useful. And now, okay, they say that cone V is called self-dual, sorry, self-similar, if there exists Euclidean metric G, which can be considered as map V into V star. So V go to Xi equal GV dot. So metric can be considered as identification vector space with dual vector space. And then we say that it is self-similar if there exists such Euclidean metric such that G with V equal V star. So, and if you consider G minus 1, to this, okay, this means G minus 1 of V star equal V. So you can find a metric such that such that if you associate any, okay, this means that you have such cone, and we choose such metric such that the only vector which have the positive scalar product with all other vectors here will be inside this, exactly this cone. So such, and all this cone is self-dual. And then theorem by Vinberg and Kircher state that the only classification of self-similar homogeneous convex cones. First of all, product of self-similar cone will be self-similar. So it's sufficient to consider indecomposable. So if V is in V is indecomposable, homogeneous cone, then V equal, then, okay, we have one-to-one correspondence with Euclidean Jordan algebra. Indecomposable also. Indecomposable algebra. And how, when we have Euclidean algebra, call it, for example, V, I made a W, even call it maybe G. Of course, we know all of them are written here. All of them are written here. So matrices, with the exception of this spin factor. So if G is such Jordan algebra, then cone associated with G consists of all, it is interior, this means you consider maximal open subset of the set of A square, where A belongs to G. So again, so for example, consider, for example, one of this algebra. Then we know that any such X, which belong to this our cone, can be written in the form A identity called E, A star, yes. Oh, no. First of all, I forget. Sorry. I forget to explain what is multiplication. Yes, of course. I forget to explain what is multiplication in this algebra. So Herm n of K is Jordan algebra, which called some standard Jordan algebra, because there are only one non-standard Euclidean Jordan algebra. It is algebra of 3x3 matrix, Hermitian matrix of octonion, because octonion non-associative, and then it is not standard. Maybe I say that if you have A is associative algebra, then we have A with multiplication will be Jordan algebra, where multiplication maybe A like this, and then A compose B equal 1/2 AB plus BA. So this is Jordan multiplication. So we consider product of two symmetric matrices such that it will be again symmetric matrices. Then we have to consider such symmetrization. So this is Jordan multiplication. And all of this.
A squared B, A equals A squared BA.
What?
This satisfies the A squared BA equals A squared BA condition.
Yeah. Okay, so but for this, for octonion is not associative, so due to this it's called exceptional. Chern algebra of dimension 27. And interesting that practical only, because in applied mathematics, they not very well knew this theory of Vinberg theory of non-self-dual, self-similar algebra, and only they consider only this self-similar algebra. And even, for example, there are some special paper where people apply this 27-dimensional exceptional algebra over Actonian for statistics. And why it is important? Why all this, in fact, all this not real case, but complex quaternion case are important, because you can rewrite all this con in terms of matrix over real number. But in this case, it will be a lot of zero. So it is sparsy. And for applications, very important, there will be many zeros. So it will be sparsy. So due to this, this rather popular. But we will see that, in fact, beside this class, if we speak about known con, which we can use for application, then there are applications also, so convex programming to integration, numerical integration of differential equation, to many other things, to some combinatoric, a lot of application. But for this, we need to know explicitly what is this con. But we will see that, in fact, beside this self-similar case, there exists only one case, which we called a special Vinberg con, rank 3 special Vinberg con. As fortunately, exactly only this con are important for supergravity. So because yeah, but in fact, now we are working about generalization of this, because for supergravity, important to have cubic. So this very important cubic, which is included into Lagrangian of the theory, such that it became supersymmetric. But we can produce this cubic in a higher dimension, higher rank, not 3 by 3, but 4 by 4 matrix also. But this is in the progress. Okay. Okay, so till now I explained this classification of self-dual algebra. In particular, this spin algebra is self-dual, and all self-dual, they are symmetric spaces. As Riemannian, first of all, I explained that. So now I consider, again, belong to Vinberg theory, which already some important part of information geometry, this Vinberg theory of convex con, not necessarily homogeneous. And this theory, it is equivalent to so-called it is exponential family of probability distribution. And this most important, most interesting part of distribution. And simplest case, even we have when you have Gauss distribution, as they call it, high dimensional, but they call it multivariable. I know some special name, but in any case, Gauss distribution not on this line, but Gauss distribution in Euclidean vector space. That this Gauss distribution is identified with space of Gauss distribution identified with this exactly this con. And also there exists some Wishart distribution also which was defined by Wishart in 20th of 19th century. and also very important for application. Also, and then people generalize a proof so any homogeneous convex cone. The theory of this Wishart distribution, which was related with this cone Pn, can be developed for any homogeneous convex cone. So due to this, a lot of application, but I will not speak this application. Okay, so now I consider some basic effect of this convex cone. So first of all, so we have a cone V, and then dual cone V star into V star. Then we can define very, very important function. Again, also, of course, in Manin, first of all, also, of course, he considers this function, which is called characteristic function. Or I'd call it also Vinberg-Koshel. Or Koshel-Vinberg. And this function on V, phi of x equal integration over V star E minus xi of x dxi. So dxi means some n form, a constant n form in dual space. So xi, xi belongs to this V star. So this is a function which very nice property, which called characteristic function. In particular, it characterizes really all this cone because where so limit where x go to boundary, limit fiat x will be infinity. And this property is very important for application to convex programming, because in convex programming, you can use the standard Newton method. So what is convex programming? You have some convex function in convex domain, and you want to find the minimum of this function. And then you can some sort of gradient method. But a little more elaborated, which called Newton method. And one of the problem of this method is that sometimes when you consider step by step apply this procedure, very elementary, which induced you approximate, first of all, you approximate your function by quadratic function. First to a term of Taylor series, and then everybody can find what is minimum of quadratic function. But then you go step by step using this Newton method, but sometimes you go to the infinity. And then people try to find modify your function, adding to this function some other function, which does not change minimum of the function, but on the boundary go to infinity. And then if you consider, and then they consider some they consider logarithm of this phi. In any case, some function which go to infinity and has some universal formula. So this is one of the applications. Yes, and other property is, again, everybody can check this very simple property that if A some transformation, linear transformation out V, then phi of A x equal determinant of A minus 1 phi of x. So in particular, if you normalize, if you assume that phi of identity equal 1, this function defined up to constant scaling, because you can change this volume form by constant scaling. Then, and if V is homogeneous, then if you take, for example, A belong to this Vinberg upper triangular group, then phi of X equal phi of A star. No, okay. No, in general, of course, we take some point, call it E, maybe. Oh, okay, you can call it E. But I did not assume that it is one of this cone. It's a general cone. In any case, we take one point and I assume that phi at this point is 1. Then we know that any x can be written A. No, E is maybe x0. A x0. Then it is A x0, and so equal determinant of A minus 1, determinant of A minus 1, all reduced to calculation of this determinant of this linear transformation. And we will see that it can be done.
That's because of using transitivity.
Because what?
Transitivity. Using transitivity, every x can be written as AX.
Yes, it's homogeneous.
It's homogeneous.
No. For yes, sure. Only for homogeneous.
Because it's written there. Sorry.
Yeah. Oh, always for homogeneous, of course. For homogeneous, all reduced to determinant. And but we are interested only in homogeneous case. Yes.
So we fix some point.
We fix some point. Assume that function is one. Yeah, then we'll reduce to this. You see, this is a relative invariant. So this, which for here. So this is, for example, if you consider determinant 1, subgroup determinant 1, which are transitive on this hypersurface, then it will be invariant. So we can call it G0. It is a subgroup, which G0. It is a subgroup of A in G with determinant A is 1. It is codimension 1 subgroup. So G equal R plus cross G0. And then we have invariant, this function invariant under G0. And in fact, all this theory can be generalized to a case when we have pseudo. Okay, maybe I say it later on some pseudo Euclidean case. Okay, so this is a property, and what we need more. Yes, and then we can, then it is relation, I forget to say that if, yes, very important, so it is Legendrian transformation. So first of all, we can say that property of this phi of x, it's a function in x, is convex, and also logarithm of phi of x are convex function. And what we need more? Just a moment. Yes. Okay, and then we have some map star from V into V star which in fact it is Legendrian transformation, which associate with X from V, associate X star, which is minus d ln of phi. So it will be one form. So, and this one form will belong to V star. And if, in general, it is not true, but if V is homogeneous, then X star equal X. It is involutive. In general, it is not true for non-homogeneous. And then we get nice interpretation from.
So what is the field which defines the inverse, which defines the star?
No,
what is the corresponding field which will bring, to define X star, you need a different.
No, you see, X point of here go to point here. This isomorphism.
Yeah, which is defined by function phi.
So then from this we got a V star, yes.
You need phi to do
And this V star will be V.
this. What is the phi which brings you from
You
V star to
change,
V?
you change places of Xi and X.
Xi is a V star.
Yes, now Xi will be a point of V star.
Yeah, sure.
And X will.
Yeah. No, so in general we have no such duality. So, but for
Well, if you have,
Okay,
if
sorry.
you have measure on V, then you obtain.
yes, no, of course we have dual measure of V star. Yes, of course. Yes, of course. All this I skip. So in fact, you see, this we have some bilinear form, one vector and one covector. And then you can do like this, but then you can consider this as a function on V star.
Yes.
So this, okay, you can integrate this with respect to X, and then you get similar expression. So it is like this. And then most important that we can define Px of Xi, Px of Xi, just a moment. Px of Xi equal e in power minus Xi x divided by phi of x. But this is by definition integral of this function with respect to Xi. So due to this, we have integral over V star of Px of Xi d Xi equal 1. So we normalize because this integral is finite. We can normalize this exponential function, and then we get probability distribution. So density of probability distribution. What is density? It is a function with integral 1. Then if you want to calculate what are probabilities that some object belong to some domain, you integrate this density, integrate this density with respect to this domain, and then you get probability. But you need that if you integrate over all space, then it must be probability must be 1. Yes, so we have measure such that measure of all space is 1, and then it's called probability measure. And so normalizing this function, we get probability measure, and what we get? We get that point of our cone parameterize some space of probability measure in dual cone. And for homogeneous case, we have dual, so we can consider a point of V star parameterize probability measure on V. And then this will be exactly, then explain why it is can be considered as part of information geometry, and also to, of course, can be for statistical physics again. It can be applied. Полчаса. Хорошо. Okay. So just a moment. Okay. Maybe then first of all, I explain what is. Yes, I can explain what are special Vinberg cone. In fact, Vinberg developed a rather complicated deep theory, but I will skip because there are many formula. But what I can explain, it's very elementary. And so first of all, here the idea of Vinberg, we already have one situation when we have x1, x2, v star. So this will be a cone, as we know, when element are vector. But Vinberg considers some T algebra. Let us consider Hermitian, already Hermitian. He defined not only Hermitian, but any algebra, but cone will be, he proves that any homogeneous convex cone can be considered as cone of Hermitian matrices for where matrices take value, where element of matrices are vector. So like in this situation. So for example, let us, and yeah, okay. So we have such x1, consider case of rank 3. So we have v1, 2, v1, 3, v2, 3. Then Hermitian, so this means v1, 2 star. So Vij belong to Vij, which are Euclidean vector spaces. And okay, v1, 3 star, v2, 3 star. So we have such matrix. And then we want to define multiplication. For example, multiplication, Jordan multiplication, if this is x, then we have defined x y equal 1/2 xy plus yx. Using the, but for this, we need multiplication of two matrices, x and y. To define this, we need define map Vij cross Vjk go to Vik. So if we define for any ijk such bilinear multiplication, then we can define some product, and we can define this product and try to generalize all this theory. And but the most important thing is that the product of this product of three Euclidean spaces, I call it V cross U cross W, must be isometric map. So this is most important property. What does this mean? This means following, that if you have V, you consider VU, go to VU product. Then it's called isometric is norm of VU equal product norm of V dot product of U. So such property. And till now, nobody knows how to describe such isometric map. But there are two special cases when it is known. So first case is the following. If dimension of V equal dimension of U and equal dimension of W, so then we can identify all of this because Euclidean spaces of the same dimension are isomorphic. Then all reduce to the situation V cross V go to V, which is isometric map. And this is and this define division algebra. So it is isometric if and only if V with this product is division algebra. And this means that V equal R C H O. And then we get a self-dual column. So in this case, we get exactly self-dual column. Of course, also this rank 2 cases, also you have spin factor, yes? Spin factor. No, sorry, no spin factor, because when we have rank 2, x1, x2, v star, for rank 2 we have no isometric map, yes, because we have only product vector with covector and the product number with vector, which are defined without nothing. So rank 2 it is exceptional, because for rank 2 we have no this isometric map. Yeah, so we need this give interpretation of this theory by theorem by Vinberg-Köcher about a self-dual case. And then there exists another case, more interesting. So second case is the dimension of U equal dimension of W. In this case, again, we can identify, and then let us call it, then I call it V equal S0 and W equal S1. Then this immediately follows that in this case, S equal S0 plus S1 is Clifford V module, graded. So for this, do I need to recall what are Clifford algebra, or it is clear? Clear.
It's clear, yes.
Clear. Okay. So we have Clifford algebra, which is Clifford algebra, which is exterior algebra with such that product of vector it is satisfies the identity. So V U dot V equal U wedge V plus scalar product U V 1. So for multiplication of vector, you use this formula, and then you can extend this some deformation of the wedge product, which became now not anti-commutative. Okay, then this isometric condition means that we have then we have Clifford V equal Clifford 0 V plus Clifford 1 of V. Any Clifford algebra admits such Z2 gradation. So this is subalgebra, it is this complementary subspace. And then we consider Clifford module S equal S0 plus S1, such that this will be graded module, of course, obvious. And then any Clifford algebra, any Clifford algebra, Clifford V is, and also Clifford V0, Clifford 0 V as the matrix algebra, I call it K of N. So A by N matrices over K, where K is, in this case, of course, K equal R C of H. Or two copy K, so 2 K of A, K of N, which is K of N plus K of N. And for this, the same. Clifford zero is the same. So there exists practically all reduced either to matrix algebra over one of this ring or direct sum of two copies of this algebra. So this classification. And this was done by Atiyah Bot Shapiro. And also we need metric to define all this. We need metric, and for all even pseudo, they give it for any signature, not only for Euclidean space, but for vector space, pseudo-Euclidean space of any signature. And we with Vicente Cortez classify all cases when there exists a scalar product in the spinor, which we consider more general situation, but for this case, we need the scalar product in, okay, you call it GS. It is a scalar product in S, such that it is S spin V invariant scalar product. And also we need that GS of S0, S1 equals 0. So they are orthogonal to each other. So all these cases were classified, so all is known. And then I can explain what are special Vinberg algebra. So this we consider Hermitian. So we consider so let us consider a case where V it is Euclidean Rn, Euclidean. But in our paper with Vicente, we generalize to pseudo-Euclidean case. But for Euclidean case, so we have Clifford V module S, and such module S is either, so there exists. So because if it is matrix algebra, then of course there exists matrix algebra act on vector. So if you have K of n, then K of n act on spinor module, which is Kn, obviously, multiplication matrix by vector. And if it is two copy, then we have two such cases when we can put one of them to 0. So if you have if it is K plus K, then we consider one copy when this go to 0, another copy when this goes to 0. So you have two. And any Clifford module, it is direct sum of if you have only one copy, then any Clifford module S will be some K, some maybe P, M, K, N. And if 2, it will be M K N plus M prime K N prime. So all is known. All is known. And now I can associate with any Clifford module, graded Clifford module S, which is written S0 plus S. No, maybe 0 plus S1, I associated vector space, Hermitian, I call it S, or maybe VS, but of course, this is Clifford V. So we need Euclidean vector space, and we need spinor module. All is known. And then it consists of all Hermitian matrices of such form. X equal X1, X2, X3, V S0, S1, and here we have dual V star, S1 star, S0 star. So dual with respect to this metric, to this metric GS. And of course, we can using first, in fact, we know that V composed with S0, it is or mu of V as 0, it is called Clifford multiplication. And this will be element of S1 because due to gradation. And similar VS1 or mu of VS1 will be S0.
What is mu?
Mu, it is a standard notation for Clifford multiplication. So you have module. What does mean module? Module means that any element of Clifford V, in particular V, S go to S. Yes. In particular, it is true for any, not only for V, for any element here, but in particular vector with product vector with spinor. It is called, I think in physics, they no, it is no, it's not okay. Clifford multiplication vector with spinor. This is exactly what we need. Yes, and then using metric, you can define all other products which we need, and then you get the algebra. This is commutative algebra with respect to commutative with respect to multiplication x y equal 1/2 x y plus y x, but it's not Jordan algebra. So here I want to say that recently, in fact, we continue. So due to this proceeding of the conference in honor of Sasha Vinogradov, we promised to write some paper, and now we are working on this paper. And it seems that we find that for any such Vinberg Hermitian algebra and corresponding con, we can get even we can define the structure of Jordan algebra. So Vinberg multiplication is not Jordan, it's not Jordan multiplication, but it seems that we can construct also Jordan multiplication.
This formula seems to be universally defined Jordan multiplication. I mean, you wrote it on the previous blackboard, and I checked it. It seems that it's just.
No, you see, for example, in fact, it is already stated in Vinberg that if it's sufficient to consider element of corresponding group G, Vinberg group, which has the form lambda 1, lambda 2, lambda 3, 0, 0, 0. This V, but I call it A1, 2, A1, 3, A2, 3. And then the only multiplication which we need is A12 dot A23 equal belong to this V13. And this is, you see, this is vector, this is spinor S0, and this is spinor S1. And so, and then already Vinberg proves that all other are trivial, and then we give Lie group structure on this, and from this you can reconstruct already for more general situation. This is sufficient only consider to find such multiplication that this will be group. Yeah, associative, exactly, associativity, yes. But in this case, associativity is trivial. Besides associativity, we need this isometric map. But this, fortunately, this automatically isometric. So this property of this so because we need not only Clifford module, we need all the scalar product which is invariant under spin, and this is classified many years ago. We classify this, and due to this, it not always exists. So in some cases there are several, sometimes no. All depend on even on signature. Or signature P minus Q. But if you consider positive defined case, it's also depend on dimension modulo 8. Okay, and so then we get only, I have to explain what are con. I explained what is space of Hermitian matrices. But then in fact, one can prove this special case. So when we consider G consists of all matrices of lambda 1, lambda 2, lambda 3, this is 0, 0, 0, A1, 2, A1, 3, A2, 3, then A act, so no condition here, and lambda I positive. Then we can define G cross Herm to Herm, which such that will be action. So this means associativity. So A applied to, no, again, in terms of Lie algebra, we have formula A. So if A belongs to Lie algebra G, Lie algebra of G, then formula will be the same as for classical case. A applied to X equal AX plus X A star. But for group, unfortunately, it is not the standard formula. For group, it is not true that A of X equal A X A star. No, this is not true. For group, it is power series in general. But nevertheless, for Lie algebra, it's sufficient. And then we have, Vinberg again, Vinberg proves this, that if you consider action of G on identity, so this identity, then it can be written as A identity A star, which of course it is A star. And this will be a homogeneous convex cone. And any homogeneous, no, it's not, I cannot say that any homogeneous convex cone, because we don't know, it is not true that all rank 3 Vinberg cone have such form. But this all which can be obtained by this, when we have, based on this case, when we have vector and spinor. So due to this, we call it special. Okay, so now I will not, we can calculate explicitly what is characteristic function, and we can describe the some three polynomial, again, according to Vinberg, of degree 1, 2, and 4, and then construct some cubic. And this cubic, which is exactly important for supergravity, and also consider the dual. In general, dual cone is not okay. Maybe this very important thing. Then, so we have the cone V, which consists of all matrices X, which has the form A star, where A belongs to G. So A has such form. And then dual cone, we can prove the dual cone V star, which is not isomorphic to this, equal, call it X prime, equal A star X A. This is dual cone. But what is more surprising is that when we consider cubic polynomial, so D of X, it is some explicit formula for D of X. And we consider cubic polynomial, dual cubic polynomial for X prime. Okay, no, first of all, we can identify using metric, we can identify Herm V, Herm S with Herm dual space of S using metric which we have here, because from point of view of this, okay, our space, what is Herm of S? Herm of S can be written as R3 R3 is this three number, real number, plus V.
They are positive real numbers. They are positive. It's not on a free. They are
No, they positive when we have group, but here not positive. No, it's not. The X3 is positive. No, they're not positive. There exists some three conditions. It's not more complicated, very complicated. So we have V plus S0 plus S1. So this is our vector space. Here we have, of course, the standard metric. Here we have metric GV. Here we have metric GS. And using this metric, we can identify V with V star, and then we can then we have two action of our group G, which consists with A, one action like this, another action like this. And they give different, it's very surprising, they give different, not isomorphic cone. But nevertheless, cubic polynomial, which are important for physics, this cubic polynomial d of x, it will be x1, x2, x, it is some sort of determinant, plus blah, 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 some cubic polynomial, then coincide with d star of x. So 5 minutes, sure, yes, okay, I was finished. And then using this, we can consider, we can describe. So the main result about application to physics is that to calculate the entropy of black hole in d equal 4 n equal to supergravity, we need consider such so-called quadratic map. This map is the form, so it is map from V to V star given by form. So we have X, and then it goes D, X, X dot. So we consider polarization of our cubic polynomial. We have some tensor with three symmetric tensor. We put two arguments equal to X, and then one remain. So it will be belong to the Herm, to dual space, Herm star. And
has one argument. This D has one argument. What's the relation with this D? And your three argument D.
Yeah, but okay, but I think I'm almost finished. And then problem to there are some formula because physicists work a lot about all this and get a lot of result. And then they also solve this problem for symmetric case. For symmetric case, they using this duality of symmetric case, when cone coincide with dual cone, they can solve this. But we can solve this for any special cone. And the problem is to find x minus 1 from V star to V, because this expression appear in the formula for this black hole. And this using this result that in fact D coincide with D star, due to this, this formula became very simple because it's almost identical. It is in any case only some scalar factor appear, but I think H minus 1 equal H star up to some function here. So H minus 1 of x equal H star of x with some function lambda of x here, which we can calculate. But since D coincide with D star, so due to this, under this identification, it almost will be only identical. So this is all what I want to say. Yeah.
Well, thanks a lot. Questions, remarks, comments?
Dmitry Vladimirovich, I have one. No, I have two questions,
Yes.
three questions. My first question is about, does Vinberg cones bring some, for example, I remember there is a both duality for 8. Does Vinberg cone make this picture more clear or no?
Which duality?
It is duality 8. Duality was periodicity 8 when you consider Clifford algebras.
No, it is not. Because
Okay.
periodicity, it is, because, it is not really, because in this special Vinberg cone, it's already, we have to fix some Clifford algebra and module. And then we are waiting. So no, of course, no relation with periodicity.
Thank you. And just at the end of your talk, you were speaking about, and you was in 1 second pronounce 3 physical words about sugar, about supergravity, about entropy.
Yes.
Can you give some ideas about black hole?
Yeah.
Can you give some ideas?
You see, this very deep theory, and this theory, most important thing and most mysterious thing is the theory, because what is supergravity, 4-dimensional supergravity? We take standard some stationary space-time, 4-dimensional, some it depends only on one function, u of x, very standard, it's stable, always the product of 3 sphere with time, and only some coefficient u of r over time, and u of r minus 1 over t. So we have only some parameter. And then what are physical fields? There are 2 physical fields. There are electromagnetic field, and also very important, we have magnetic charge. So electric charge and magnetic charge. And beside, and if you have only one electromagnetic field, then you know that you have star, Hodge star, which can interchange between, you have this electromagnetic field F and the star of F.
Okay.
And you can rotate, and this is how it's called, some rotation. But if you have many fields, then there's no Hodge star. And to define this Hodge star, we need to consider scalar field. And scalar field take value if we have 5-dimensional case, then it take value exactly in the determined hypersurface, determined equal to 1 in the Vinberg cone. But if you consider 4-dimensional, you have to consider R map, and then instead of you have to consider some special Keller manifold, which is a mathematician Petetsky Shapiro discovered it many years ago in 60s, before all physicists. And this is very simple. It is called Ziegler domain. And what is Ziegler domain? The tube domain, very simple. Ziegler domain, so you have Vinberg cone, and you consider Rn plus IV in Cn.
Yes.
So this V belongs also to Rn. And this is Ziegler domain. And then scalar field take value in this Ziegler domain. So you have, and using this, you can define this Hodge star, which important for physicists to get this generalization of this rotation between, so if you have F and star of F, then you can consider the cosine some lambda plus sine lambda, okay. So you can rotate. So F and star F, it is well known, they are, so you can interchange, you have electric field and magnetic field, E and H. And but then you can rotate such that electric field become magnetic and so on. But of course, for this you need magnetic charge.
Yes.
And most important and most non-trivial thing is that besides this field, there also exists a central charge, which developed by Witten,
Yes.
which is very mysterious. And this is a function which depends on radius of black hole on one parameter with complex value function. And then, and this crucial for all this theory. And all reduced to you see, here you have this Vinberg cone, and all reduced to this Vinberg cone, and to Vinberg cone, all reduced to this H to this map,
Okay.
which associated with cubic polynomial.
Okay, I think you can continue after
Yeah, okay,
the
I see.
seminar. And I believe it's time to finish. Thank you very much for visiting this session, and we hope that we meet in a week at the same place. The next talk will be by Valentin Lichagin. Thank you very much.
What is his title?
Well, you will receive the
Okay.
announcement today,
Okay.
tonight.
Okay.
Okay, thank you. Goodbye.
Thank you.